It's a good coffee. All the information that we provide to a computer are eventually treated as zeros and ones. However, their logical orientation and treatment are never same. For example, if you consider a bank account and the associated information with it, let's say account number, account name, and account balance. The account number can be a whole number, the account name can be a text, and account balance can be a fractional number. Have you ever wondered how these different types of information are managed inside a computer's memory? Coming up. Hey, this is Subrata Kumar Dey and welcome back to Strictly Coding. I am a university teacher teaching computer science courses over a 1.5 decade. If you are a programming enthusiast and new to this channel, consider subscribing and press the notification bell so that you don't miss anything. Today's video is divided into 3 segments. In segment 1, I'll be talking about the constant, which enables programmer to infuse data or information directly into the source code without involving any additional memory. In segment 2, I'll be talking about the data type, variables, and some associated terms which we need to understand. In segment 3, I'll be explaining the fundamental data types available in C++. Sometimes we call them primitives, to deal with character and numeric data, including, of course, the whole numbers as well as fractional numbers. But to represent a text which is a collection of characters, we have several non-primitive choices. Either we can use a string, we can also use a character array. And the third choice can be using pointer to character. However, the array and pointer themselves demands individual videos to understand them clearly. So therefore I am not going to explain the mechanism of an array, how it works, and why we need pointer and how to deal with that. I will dedicate separate videos for that. So if you are a subscriber, you will be notified on time. Last but not the least, there is a bonus segment which explains why different data types has different memory requirements. So let's begin. Now, as usual, if you have seen my previous videos, if not, please see the card here. I have created a code blocks project to explain all the relevant concepts that we are going to cover in this video. In the first segment, first I'm going to explain what is constant. So constant is a fixed value that is decided by the programmer and that is embedded or infused within the source code. For example, if I say, in this case we have declared 2 integers x and y. Now if I say x equal to 100, now in that case the value 100, which is a fixed value decided by me, the programmer, is going to be used in this statement. Okay, so what we are doing here, we are actually storing that 100 into x. On the other hand, I could also say, for example, y equal to x plus 30. Now in that case I am using 2 operands. The one value, the first operand is coming from a memory location represented by x, and the second operand is 30, which is not coming from any memory location, which is a constant, okay, fixed value, literal, given by me, the programmer. So that is actually constant. So the value of y will be 100 plus 30, 130. Okay, so this is a numeric constant. Similarly, we can have character constant, which is represented within single quotation. For example, character ch equal to the character a. So if I use the character inside a single quotation, it becomes a character constant, okay, character literal. So I'm assigning it as the initial value to a character. Similarly, to represent fractional values, we can have float or double. I'll be explaining all this, don't worry. And here I can say equal to let's say 3. So pi is let's say 3.14 something. Okay, so f. Okay, so the suffix f represents that 3.14 is a floating point number, and instead of taking the input from user, or instead of reading the value from some memory location and assigning it to float pi, as a programmer I am deciding the constant value. Okay, so literal, so that is a floating point literal. Okay, similarly, if you want to represent a text, then we have to use it within double quotation that we'll see. For example, we are printing enter and int semicolon. Now this whole thing is treated as a fixed text that will go for output onto the to be shown onto on the screen. So this is a string literal. Okay, so that is all about constant. Okay, now you can assign some literal to some variable, and you can declare this variable itself as constant. That means now the value of that memory cannot be changed. Okay, but that's a different discussion. Okay, now let us talk about what is data type and what are the different types of variables available in C++. Okay, now when you talk about data type, if you recall that bank account example, the account number can be a numeric value. Okay, the account name can be a text, the account balance can be a fractional value. If you want to represent the gender with only F or M to represent male or female or male, then that F or M can be a character. So depending on what type of data we want to store, we need to first reserve memory in our RAM to store those data, future data. Okay, so before we store anything into the memory, we have to reserve the memory. Okay, now the data type actually tells how much memory to reserve for different type of data. Okay, and when we declare a variable that is an instance of that data type, when program gets executed, memory will be first allocated for that type of data, because from the type it knows how much memory is needed, and that variable will be named to that memory. Okay, so variable can be thought of as a named memory. Okay, so for example, if I want to store a character, now I have given a byte into the RAM, or if I am trying to store a whole number, I'm given 4 bytes maybe. That depends on the compiler and the platform. So let's say 4 bytes are given to store a number. Those bytes can be byte number, let's say 100 to 103. So if the name of the variable is x, then x represents the byte number 100. Okay, so variables are nothing but named memory. Okay, now in C++, there are some fundamental data types. We call them primitives, and typically they are used to represent a character and numeric values. Okay, now when you say numeric values, they can be the whole numbers, they can be fractional numbers. Now if you look here, to represent a character, the data type is char. So someone pronounce it as char, someone pronounce it as char, whatever, and we have to give a name to the memory to represent, to store a character. So now ch is a variable which can store a character inside the memory, because the data type of ch is character. Okay, similarly, x and y are two integer variables, because their data type is integer, so they can store two whole numbers, one in x, another in y. So when you talk about numeric data, if it is whole number, then we can declare them as integers. Of course, there are variations of integers like short integers, long integers. Okay, and also they can be signed, means they consider both positive values and negative values, they can accommodate. If it is unsigned, they can accommodate only positive values. But I am not going to discuss them right now, maybe later on. Okay. So for fractional value, we have two types, float and double in C++. For numeric value, we have int. Also, we have short and long. Okay. I just forgot to include short here. Now, if you think about large numbers, then we can use long, and if the number is very large, then we can use long. Okay, so we can use the long qualifier with long itself. Okay, so that allows us to accommodate very large numbers. Okay, so this int, short, long, and long represent whole numbers. Okay, the char or char represents the character, and bool is a data type which actually allows us to store two possible values, either true or false or yes or no. Okay, so it only can have two states. So if that is the scenario, then we can use a variable. In this case, status is the variable and whose type is Boolean, and now we are assigning a literal false, which is nothing but 0. Okay, so if you assign true, which is nothing but 1. Okay, now how to represent text? Now when you talk about text, we do not have any primitives to represent text, but there are non-primitive ways. Okay, so one of the most popular way is string. So string also is a data type, but this is not fundamental data type. String is a class. Okay, but we will dedicate different video to explain class. Right now you understand string also is a type, so therefore some text becomes a variable of string type, and here we are assigning some string literal fixed value as a programmer, because we are allowed to do so, to this variable some text. So if you look at these following statements, in the first we are asking user to give input for an integer. Okay, so that is why we are writing C in X. Okay, because we have declared X as an integer. Similarly, we are taking input for a character, so we are prompting user enter a character, and we are taking input from keyboard a single character. Okay, then we are asking user to give input a long number, large number, fairly large number, whole number, and then we are asking user to give input a very large number, so that's why we declared LLG as long. Okay, so this X LG for long and LLG for long will be storing some numerical whole numbers, and the CH will be storing a character once the inputs are given from the keyboard. Now let's talk about these fractional data types. So as you see, float pi is declared as a float variable, and double pi is declared as a double variable. So now both float pi and double pi can store fractional values. So we know that pi is a fractional value. So as a float, we are using again float literal 22.0 divided by 7.0. It is important to treat them as fraction, otherwise division will discard the fractional result, if any. So if you simply say 22 divided by 7, both 22 and 7 are whole numbers, so result will be 3 point something, but it will be treated as 3. So therefore, if our division produce a fraction, so we need to treat at least one of the operands as a fraction. So in this case we are telling 22.0, and also we are using the qualifier f that actually indicates that okay, this is a floating point fraction. Okay, now I'll explain what is the difference between floating point and double. Okay, these are nothing but the difference in the precision. Okay, so double has the double precision after decimal point than a float. Okay, so both float pi and double pi stores the value of pi. Now if I show you in calculator the value of pi, if you see here 22 divided by 7, and the value of pi is this 3.7 142857, 142857, 142857. So after decimal point 142857 is recurring. Okay, it's repeating again and again and again and again. Okay, infinite times. So that is the value of pi. But the more digits you take after decimal point, more accurate value you get. But we will see that the double pi will give us more accurate value than float pi, because double pi has more precision when we execute this program. Okay, now we have taken all the inputs. Now we are actually showing the user what were the inputs given. So we are printing the int semicolon x equal to, it will be printed as it is, and we are printing the variable. So at runtime it will be detected that this is a memory location of an integer, so it will read the content from the memory as a whole number and it will print that, okay, on the screen. Similarly, we are printing the ch, which is a character. And now in the line number 28 we are printing the float pi as well as double pi. Both of them should print the value of pi. But as I said, the float has less precision and double has double precision than float, so double will give us more accurate value. Okay, so I'll come back here when I execute this program. Then we are printing the value of long, which is LG. We are printing the value of long, which is LLG, and we are printing the value of the Boolean variable, which is status. Now if you recall, we have stored false into the variable status, okay, but anyway it is nothing but 0, that we'll see in the output. And we have stored a string literal in a string variable some text, okay. So we are also printing the value of some text from the memory location represented by the string variable, which is also can be called as an object, but I'll explain what an object and class is in a different video. Now, so this is one of the way to dealing with text, which is using a string, okay. So some text is a string and we have used some text to represent the text. Another alternate way of representing a text is a collection of character. Now you see the data type is character, but it is now collection of 50 characters. So we can also store a text inside this collection called array, and the name of the array is the name, okay, which is capable of storing 50 characters. So we are asking enter your name and we are taking input into that array, and I'll show you that the input is stored in the name and we can actually printing that array, okay, as a collection. However, there is a limitation in the array, character array, as well as a string. If you give space, your name can include space, okay, like in my case Subrata Kumar Dey, so my name has 3 words including 2 spaces. So if we want to provide space, then there will be a problem, but of course there is a remedy to deal with that. We'll talk about that later. Okay, so now let's try to execute that. So if we build this and execute, I'll show you the source code and the output window side by side. So the very first thing we are showing to the user, we are prompting user enter an int, okay, so that's why it is showing. Now if I give the value 12, this will go to the integer variable x, okay, so it is stored into that memory, okay. Now, and which is 4 bytes typically. It can vary depending on the compiler version and your platform. Okay, now it is asking enter a character, so I can only give one character, okay, so let's say capital A, and it is working fine. Now it is asking enter a long variable, okay, so a long variable can be a pretty large number, let's say 1 2 3 4 4 5, okay, so I give a long number, 8-digit number, and that's fine. So this 8-digit number is stored into the variable LG. Okay. Next we are taking input for a long number, so I can give even bigger input. Okay, so let's say 12-digit number, which is pretty big number. Okay, now this very big number cannot be accommodated in a long or an integer, but can be accommodated in a long. Okay, and that's why it is working fine. It did not give any error. Okay, and now it has done some calculation. It has calculated the value of float pi and double pi, and now it started showing the outputs. Okay, so if you look at the source code, the first thing it shows from here, the int x equal to 12 according to our source code. If you see here, okay, so int x equal to 12, and then character ch equal to the value of ch, which was a, so a is printed here. Then now interestingly, if you look at the next output, we are printing float pi equal to, in line number 28 in the source code, if you see, float pi equal to the value of float pi, comma, space, double pi equal to the value of double pi. So float pi is a float variable, double pi is a double variable. Now both float pi and double pi stores 22 divided by 7, so they should store the same value. However, as I said, float has less precision than double precision, so double will give us more accurate value. So if you see here the calculator, we have already calculated the value of pi, which is 3.142857, 142857, 142857, so on. So if you look here in the output window, 3.142857, that is fine, but after that it does not give us the correct output. Okay, so instead of 074737, it should have been 142857. On the other hand, if you look at the double pi, the output is 3.142857, 142857, okay, then 1, and it continues with the correct output because its precision is much higher. Okay, so a float variable gives you typically 7 decimal place precision, okay, after the point, including point, and the double variable gives you 15 decimal places precision. Okay, so that is why after 7-digit float started give us some wrong value. Okay, so that is the thing. So if you need a more precise value, especially if the data represents is used for some scientific calculation where the precision is extremely important, then you can use double. Okay, on the other hand, if the fractional value represents some mundane everyday life information, like what is the balance, account balance, now it can be 40,062 and 50 cents, or you can simply say 52 cents. You don't need to say dot. Okay, so 0.5283, so you don't need to show so many decimal points to represent the cent. Okay, so float is good enough. Okay, now for long it is also showing the 8-digit number. Okay, and for long it is also showing that 12-digit number that we have given as input. So our input was properly correct, and the memory allocated were capable to store these large values. Okay, we have also printed the Boolean status. So you see here status cout. Okay, so Boolean status equal to the value of status, so we know we stored false, but it is printing actually 0. Okay, because false is nothing but internally treated as 0. And we have also printed the string, okay, so which is some text. Okay, so we have initially assigned a string literal into that string some text, so therefore the output some text. Okay, and finally we are asking user to enter a name, and that we are going to store in a character array instead of a string now. Okay, so we will give the input. Now let's say my name is Subrata Kumar Dey, so Subrata, Now if I give space, it will be a problem, but I'm not going to explain it in this video now. I'll do it later. So if I press enter, now Subrata was successfully stored in that character array called name, okay, and the output is successfully printed. So name equal to the value of name, which is Subrata, okay. So that is all about data types. Now, as the bonus section, I said why different data types requires different memory size, okay. To explain that, let me try to give some unfavorable input and let the program behaves in an unexpected way, and then I'll talk about that. So let's say I want to execute the same program once again. So it is asking for an integer, okay. Now if I give an int, if I give a, let's say 10-digit large number as an integer, let's say 8765432 5, okay, 10-digit number, will it be stored in an integer or not? So as I said, okay, let's see, let increase the number some more. So it is not accepting, okay. So therefore it should have asked enter a character, enter a long, see, it skipped all of them, okay. And it is showing some weird output as X, but we have given this 876543255. Instead of that, it is showing some unknown numbers, okay. So that means when we declare a data type, every data type has a capacity, okay. What can be the maximum value it can store, what can be the minimum value it can store. So if we cross the limit, if we are trying to store something which exceeds the capacity, then this will happen, okay. So that is why you need to understand what is the sweet spot, what are the correct amount of memory that is given to a particular data type, okay. So for that, let's see the chart here. Now if you look at the chart, you see in the character category the data type is char or char, whatever you pronounce, and if it is a standard keyboard characters, English characters like this keyboard, then it actually need 1 byte, okay. However, we can also have different types of character which are characters associated with other languages like Spanish, French, Chinese, okay, Hindi, Bengali, etc. Then we need to use Unicode character, okay. So that will take more than 1 byte, okay. But let's talk about this particular standard English keyboard character, and we call that Ascii character, okay. When you talk about numeric value without fraction, we can have short, int, long, and long, okay. And depending on what data type we are declaring to represent a numeric whole number, it can take 2 bytes, 4 bytes, or 8 bytes, okay, depending on your compiler and the platform, okay. But it stores a whole number. When you talk about numeric value with fraction, we can have float double as well as long double, and that also can take up to 4 bytes, up to 8 bytes, either 4 bytes or 8 bytes, okay. If we use float, then it has precision of 7 decimal point. If we use the variable as double, it has precision of 15 decimal point, and we have seen that demonstration in our output, okay. There is a Boolean which actually stores zeros and one, okay, yes, not, kind of, and also there are some other types, for example void, which don't represent any data, but it actually needed to indicate the return type of a function. If you are not familiar with function, please check the card above to look into the function videos. And also there is a null pointer type which represents that a pointer is not pointing to any valid memory, but again I'll be publishing several videos on pointer, okay. So why character 1 byte? Now if you consider this keyboard, how many characters it has? Not much. If you consider capital letter, small letter, digits, all the operators, all the parentheses, okay, punctuation symbols, and all the characters, if you combine them together, they will not exceed 200 characters, okay, that you can visibly see on a standard English keyboard. So if you use 1 byte memory, we know that memory is a collection of zeros and ones. Logically, it is represented that way. Physically, it can be electric charge or magnetized state, okay, of a magnetic disk, or a laser burn on an optical disk, okay. But however, logical representation is zeros and ones, any data. So if we say the byte is a collection of 8 zeros and ones, so we call them bit, but byte is the transactional unit of memory, okay. So if you want to use memory in terms of memory, you cannot say I need 1.5 bytes, no, either 1 byte or 2 bytes, okay. So byte is the transactional unit of memory. So if you allocate 1 byte memory, then you can only store 8 zeros and ones, okay, combination of zeros and ones, 8 of them, okay. So the lowest combination can be all 8 zeros, and the highest combination can be all 8 ones. Now again, if I show you in the calculator, if you see here, if I go to the programmer mode, we know that we have many different number systems. So on our everyday life, we use decimal number system, but since it is zeros and one, it is a computer use binary number system. Okay, so if I give all ones, 1, 1, 1, 1, 1, 1, 1, 1, all 8 ones, that is the highest possible configuration of zeros and 1, providing highest value, and the decimal equivalent of that value is 255. And in binary, if you put all 8 zeros, which are basically 0, so in decimal also it is 0. So the lowest value, the decimal equivalent of the binary combination, the lowest possible value of those combination can be 0, and the highest possible combination can be 255. So basically we can have 256 unique values, okay. We can represent 256 unique values in 1 byte. I hope you understand. Now why 256? Because in binary the base is 2 and 8 bits, so 2 to the power 8 is 256. So if I show you, if I go back to the standard version, scientific version, so 2 power, sorry, 2 x to the power y 8, so 2 to the power 8 is 256. For character 1 byte is fine because we do not have 256 visible characters here. So 1 byte is enough so that we can assign each value to each of these characters uniquely, okay, without any conflict. And that is why the Ascii character actually occupies 1 byte. Now if you allocate 1 byte to store an integer, okay, whole number, then the highest value you can store is 255 and the lowest value can be 0 because the capacity of 1 byte is 256. But when you talk about signed number, it also can include negative values. So now your range starts from negative side, but maximum of them are higher than 255, or if I consider the sign, then higher than 127. Then how can I store them? I cannot. Now if you increase the capacity of an integer, size of an integer from 1 byte to 2 bytes, then what is the range? Okay, so again 2 to the power 16 gives us 65,536. Now if we take the signed number, if you split it from the negative side, so we get divided by 2, so our range becomes minus 32,768 up to positive plus 32,767. So the highest value we can store in an integer, if we use only 2 bytes for an integer, will be 32,768. But we can have many numbers which are much bigger than that. For example, you have a identification number which is 8 digit. So you cannot, or even if it is 6 digit or 5 digit number, but which is more than 32,768, you cannot store that. So you need more bytes. Now if you take 4 bytes, then it will be, the range will be 2 to the power 4 bytes means 32 bits, so 2 to the power 32. Now you have, you see, almost 4.2 billion. Okay, so if you take a half in the negative side, so now your range is minus 2.1 billion up to plus 2.1 billion, so your range is 4 billion. Okay, so now most of the numbers that we deal with actually falls into this range. Okay, so 1 2 3 4 5 6 7 8 10 digit numbers, but the highest value of this 10 digit number can be 2.1 some billion. Okay, you cannot store 4 billion or 5 billion okay, the 10 digit number, but outside of the range. So if you use, let's say, 8 bytes, then 2 to the power 8 means 64 bits. Now you see, sky is the limit. Almost any large number you can think of can fit into a 8 bytes. So that is why long allows you to store very large number. Okay, so definitely long gives you the higher range, then integer gives you the higher range, then short, and long gives you the maximum capacity to store a very large number. Now in reality, this type of large numbers requirement will be very less. Okay, maybe 0.00001% of time you need to store such a large number. So that is why if you declare all the numeric whole values as long, you will be wasting a lot of memory location, because 8 bytes for each long. But maybe your number is too small, which can be accommodated in 2 bytes. So therefore, the sweet spot in most compilers, the sweet spot for an integer is 4 bytes. So most of the numbers in everyday use fits within the range from negative 2 billions to 2.1 billions to positive 2.1 billions. You can actually increase the range without increasing the memory, just by telling that my number is an unsigned number. So if you don't say anything, it is signed. That means it considers both negative and positive range. But if you say instead of telling int x, if you say unsigned int x, then it will still be 4 bytes, but now the range will be from 0, because now it will treat only the positive values. Okay, so now your range becomes 0 to 4.2 billion instead of negative 2.1 billion up to positive 2.1 billion. Now it becomes 0 to 4.2 billion. So that is another way. So if you're very sure the type of data that you are going to store in this variable can never be negative, so you can simply declare that as an unsigned, and still you can increase double the range. Okay, now for float, typically it takes 4 bytes, and for double typically it takes 8 bytes. Okay, so 4 bytes means 32 bits. Among those 32 bits, I think 7 bits are for representing the exponent part. Okay, and here 15 bits are used to represent the exponent part. Okay, in case of double. Hope this helps. If you have liked this video, please give a thumbs up and share with your friends. And what do you think? Do you think that 4 bytes is a good choice to store numeric value, whole numbers? Or should we always use 8 bytes to store whole number? Or we should use 2 bytes to store a whole number? Which is the sweet spot? What is your opinion? Comments below. I'll try my best to answer you. And thanks for watching. See you in the next video. Have a wonderful day.